consider a case in which you have a weak acid, which is titrated by a strong base. Check what the pH might be after the addition of only 10 mils of 0.1 molar sodium hydroxide solution to those 25 mils of 0.1 molar acetic acid solution. Then check the pH after the addition of 25 mils of sodium hydroxide and then 35 mils of sodium hydroxide. So you want to first consider the basic reaction that's occurring. Having acetic acid and adding sodium hydroxide to that, you're going to have a neutralization where the sodium hydroxide will deprotonate that acetic acid, leaving you sodium acetate and water. This is one way to view it in the molecular equation, but you can also consider the net ionic equation, in which sodium hydroxide first breaks up into two ions, sodium ion and hydroxide ion, and then that hydroxide ion strips a proton from acetic acid, leaving acetate and water. So you would like to determine what will be the pH after the addition of a certain amount of hydroxide. Now, being that you do not have equal volumes of the acetic acid and sodium hydroxide solutions, nor equal molarities, actually, you cannot predict how much of one will react with another by molarity, but instead you must predict how they'll react with each other by the number of moles of each compound. And so you want to calculate the number of moles of acetic acid and then hydroxide. You're using the ICF table. And so to find moles, do molarity times liters, so you get the following number of moles. And then having a strong base and being that it reacts 100% with this acetic acid, it is all going to react. So the change in the number of moles of hydroxide will be the same as the change in the number of moles of hydroxide that were added, being that this is the limiting reagent in this case. And so you'll be left with no hydroxide left over and only acetic acid and now acetate. Now, having these number of moles of both acetate and acetic acid, having only changed or having some ratio between this weak base and its conjugate's weak acid, we can use the Henderson-Hasselbalch equation. And so we'll say pH is equal to pKa plus the log of the base over the acid. Now here, technically, we should be using the concentrations, the molar concentrations of our base, acetate, over our acid, acetic acid. Now, those concentrations are going to give us a ratio of their concentrations within this new combined solution, which we'll then take the log of. And so you can find those concentrations by taking the moles over the total number of liters. Now, we had 25 mils of the acetic acid solution, and then we added 10 mils of the sodium hydroxide. So we had a total of 0.035 liters. So we can plug in the molarity here, but you see that having the same number of moles at this location and as at this location, actually liters at this location and this location, the number of moles, one versus the other, is going to have the same ratio as the molarity, one versus another. And so you could save a lot of time just by plugging in the mole-mole ratio into this instead of molarity-molarity ratio. Either one will work here. So you find then the pH of this solution is 4.56 after adding some small amount of sodium hydroxide. What if, however, 25 mils of that 0.01 molar hydroxide solution is added? Well, then you'll have the same number of moles of hydroxide added as the number of moles of acetic acid were there. Now, both of these you might consider to be the limiting reagents, so we could say that both of these are going to be completely consumed. The hydroxide is going to lose 0.0025 moles of it. Similarly, the acetate will lose the same amount. Being left with none of those and only now acetate left over. It's as if you've got now just a solution of sodium acetate. It's as if you had just put sodium acetate into water and this titration had never occurred. Now, having just sodium acetate, having just this basic salt present, you should expect to have a basic solution. What will be the pH of this now basic solution? Well, you've got the acetate, but you should treat this now like an ICE table, not ICF table, being that we're not adding a strong acid or base here. So you need to use molarity here, not moles, and you can find, using the standard ICE table to find the pH of a salt solution, you can find that the concentration of hydroxide is going to be X, and solving for that gives us a value of hydroxide being equal to 5.26 times 10 to the negative 6. We were able to do this because this equation up top was governed by the Kb expression. Do you see how this acetate is acting as a base in water? So this equation is governed by Kb, and oftentimes you may not be given the Kb of this compound. You might be given the Ka of the acetic acid, which is 1.8 times 10 to the negative 5. So you might be able to find the Kb by dividing by the Kw, 1.0 times 10 to the negative 14. So you use this Kb here. Okay, so please note that we have at this equivalence point where we've reacted just enough hydroxide to react with all of the acetic acid, we have now got a solution with a pH which is greater than 7. At this equivalence point, in this weak acid, strong base titration, we've been left with now a basic solution. The pH is greater than 7. This is because there's some conjugate base of the weak acids still left over. It's as if we just added some a basic salt to water. So you'll need to be able to explain why you have the basic solution, and it's because we have this conjugate base of a weak acid left over. This is the central reason, although it's easy to memorize that you'll have a basic solution when you have a weak acid strong base titration at the equivalence point. See how it has a strong base and a weak acid. It's likely you'll have a basic solution at the equivalence point. Continuing on. Now what if we had added so much hydroxide that we passed the equivalence point? Now adding hydroxide, adding the strong base, you want to use the ICF table, use moles of all these things. Now here, in this case, your limiting reagent is the acetic acid. And so it's going to be all consumed, and you're going to be left with now hydroxide left over and some acetate as well. So what will be the pH of this? Well, the pH is not going to be very much affected by the presence of this weak base, this acetate. Instead, the pH is largely governed by the presence of this strong base. Yes, it would be quite complex to find the pH of the two of these things, and so we just make some presumptions and say that the pH is only governed by that strong base left over. And so consider then that you have 0.0010 moles of that hydroxide, and divide now by the new combined volume to get the molarity of hydroxide, and hence the POH and then the pH. Okay, so we can see that for this weak acid strong base titration, initially we have an acidic solution. It's not particularly acidic, being that it's just a weak acid that we have. And as we add strong base, the solution becomes less and less acidic, or more and more basic. It approaches 7, but goes beyond that before we reach this inflection point, the equivalence point. The equivalence point is at a pH of greater than 7 for this weak acid strong base titration. Please note then that having just a lot of hydroxide present, just a strong base primarily present and relevant, we're going to have a quite basic solution eventually, closer and closer to 14, as we add this sodium hydroxide to the solution. And so kind of a summary of kind of a lot of calculations. What if nothing is added? What if there is no titration? I only ask, what is the pH for some weak acid or base? Well, you can use the equilibrium expression and the equilibrium constant to do that. However, if you have both a weak acid or base and its conjugate, a ratio between those two, then you can use the Henderson-Hasselbalch, which is quite simple. quick and easy. Now, if you're doing a titration, in a simple case, a strong acid, strong base titration, you are going to have having some strong acid left over, just having the concentration of that strong acid, the pH. But having some strong base left over, having the concentration of hydroxide, you can find the POH and then the pH. But what if you have either a weak acid strong base titration or a strong acid weak base titration? Well, you need to use an ICF table if you're adding either a strong base or strong acid to a weak acid or base. ICF table first, and then depending upon what's left, you have to follow different pathways. If you've just changed the ratio now of your weak acid or base and its conjugate, both of those are present and none of the strong acid or base is present left over, then you'll use the Henderson-Hasselbalch equation. If you've reached the equivalence point, so that it's basically just some salt left over from the initial weak acid or base, then you can use an ice table. And if you've added so much strong acid or base that's still left over after the equivalence point, and the other weak acids or bases are no longer relevant, then you just find the pH or POH, ignoring the presence of the weak acid or base. Thanks for watching, guys.